Tyre, and today I'll be teaching you about horizontal and vertical tangent lines. And to do this, I'm using a cool program called GeoGebra. You might have heard of it, probably have. And with this, you can use mathematical formulas, and it'll display them for you. And so here I've made a solar system, or a model of it. And it's not perfect because the solar system actually has elliptical orbits, but for our purposes, circles are fine. And the cool thing about GeoGebra is you can animate your creations. And so, that's just a cool trick. And you can see the planets rotating around on their orbits. And now we'll get to the mathematical part. One second. Okay. So looking at this, we can see that there is tangent lines on Earth, Uranus, and Jupiter. And a tangent line is basically a line that only touches a curve at one point. And even when you zoom in really close, you can see that only at that one point does it touch the curve. And this means that tangent lines are always perpendicular to the curve at the point that they touch. And using calculus, we can determine the exact positions of these curves using the formulas of circles. So for Earth, the formula would be x squared plus y squared equals 16. And this is just standard circle form. X squared plus y squared equals the radius squared, and the radius is 4 in this case for Earth, and 4 squared is 16. And we derive this implicitly, which is 2x plus 2y dy over dx equals, and then the derivative of a constant is just 0. And using some algebra, we find that dy over dx equals negative x over y. And alright, to find there are two types of tangent lines. One that are useful to us. One is the horizontal tangent line, and then one is a vertical tangent line. And to find a horizontal tangent line, we use the numerator, which in this case is negative x, and we set it equal to 0 because the slope at that point would be 0, right? Alright, and we can see that there'll be 2 points where there'll be a horizontal tangent line, one right here and one at the top. And when we plug it back into the original formula, we get 0 squared plus y squared equals 16. And so y equals plus or minus 4. And so our horizontal tangent, or tangents, are at 0 and 4, and 0 and negative 4. And you can just kind of convert this to the graph at negative 4 and 4. And then to find a vertical tangent, you equal the denominator, which in this case is y, to 0. So 0 equals y. And then you plug that back in the same way, and you'll get x squared equals 16, which is plus or minus 4. And so our vertical tangents are at negative 4 and 0, and at 4 and 0. Pardon my bad handwriting. And you can see on the graph, because this is a simple one, that the vertical tangents would be at negative 4 and at 4. And you can use the same method for any circle. So say for Jupiter, which is x squared plus y squared equals, and then the radius squared, which is 64. And we do the same thing and derive implicitly and then we'll find that the constant will still derive and equal 0. And this should be looking familiar, because when we, my bad, dy over dx, and we'll find that the derivative dy over dx of any circle with centered on the axis, the origin, will have a dy over dx equal to negative x over y. And the reason being that the radius squared, when you derive it, it'll always equal 0. But what will change, alright, so let's go through the same process. So finding a horizontal tangent, you equal the numerator to 0. So negative x equals 0, and then x equals 0. And we plug that back in, and we find that y equals plus or minus 8. So even though the dy over dx is the same for all circles, the positions of the tangents will not be the same. And so when the horizontal is at 0 and 8 and 0 and negative 8. And this is apparent because at this point the tangent will be horizontal. And it'll get a little redundant, but you can do the same thing for the vertical tangent, equaling the denominator y to 0. And alright, let's say that there's a bit more complicated. So bear with me while this saves. Alright, so now we have a new graph. Let's say it's 3x squared plus 5y cubed equals 4. And this is kind of a strange looking graph, but just like any other, we can find the horizontal and vertical tangents by using calculus. So 3x squared plus 5y cubed equals 4. And we derive this implicitly. So 6x plus 15y squared equals, and then derivative of a constant, 0. And we manipulate this. Oh, and my bad, dy dx. So dy over dx will be equal to negative 3x, negative, my bad, 2x over 3y. Over 5y. My mistake. Alright. And to find the horizontal and vertical tangent, so the horizontal you find, you equal the numerator to 0. Like 2x equals 0. Wait, this was a squared. Alright, can't forget that. And we'll find that x equals 0. And we plug that into the original equation, so 5y cubed will equal 4. And y cubed will equal 4/5. So y equals the cube root of 4/5. Alright, and on the graph it's apparent that there's only one horizontal tangent, and that would be at this point right here, which is the 0 and cube root of 4/5. And so a horizontal tangent is at 0 And the reason that this one's not plus or minus is because it's a cube root, and so there'll be no plus or minus. Right. And then for the vertical tangents, we equal the denominator, 5y squared equal to 0. And when we plug that in, we get 3x squared equals 4. And so x will equal plus or minus this time because it'll be the square root of 4/3. And so our vertical tangents are plus square root of 4/3, 0, and minus square root of 4/3, or negative, and 0. Alright, and we can see on the graph that at negative 4/3 comma 0, there'll be a vertical tangent right there, and at positive 4/3, positive square root of 4/3. And so yeah, this is a useful tool in calculus, deriving implicitly, and then equaling the numerator to 0 to find horizontal tangents, and then the denominator equal to 0 to find vertical tangents. I wouldn't be able to do this without the help of GeoGebra, so thank you to those developers, and I'll see you next time.